Previously, we already discussed on the definition of Laplace transform. So now we will take a look at the properties of Laplace transform. We start with the linearity property. So if I have three functions, let's say f, f1 and f2, and for these three functions, the Laplace transform exists for s greater than a, and let c be a constant. So if I have addition or subtraction of this function, let's say I have f1 plus minus f2, and if I want to find the Laplace transform of f1 plus f2, it is equal to the Laplace transform of the first function plus or minus the Laplace transform of the second function. And if I have a constant c multiplied to a function, the Laplace transform will be equal to c Laplace transform of f. Right? So, let's try to take a look at this example. So, let's say I have to find the Laplace transform of addition and subtraction. So, I have Laplace transform of 1 plus 5 exponent 4t minus 6 sine 2t. So I have three functions. The first one is constant, the second one is exponential, and the third one is sine. So by the first property, we can separate the function first. Okay, so I have, what's happening here? So I will have Laplace of 1 plus Laplace of 5 exponent 4t plus Laplace, it should be minus Laplace of 6 sine 2t. Okay, so Laplace of 1, you can refer to the table. So 1 is a constant, so you get, okay, from the table, where's the table? So a constant a, the Laplace transform will be a over s. Okay, so I will have equal to 1 over s. For the second Laplace transform, I have 5, where 5 is just a constant, so I can take out 5, Laplace transform of exponent for t. And for the third function, 6 is just constant, so I can take out 6. So Laplace transform of sine 2t. Okay, so now, if I see here, we can refer to the Laplace table for exponential and sine. Okay, so for exponential, at, it is 1 over s minus a, and okay, so this one. And for sine, it is equal to a over s square plus a square, right? So for this exponent, my a is equal to 4. A equal to 4. So I have a 5 multiplied by 1 over s minus 4. Minus 6. For this one sine, my a is equal to 2. So it will be 2 over s square plus 2 square. So the final answer will be 1 over s plus 5 over s minus 4 minus 12 over s square plus 4. Right? Okay. So that is how. So in this question, they don't ask you to use the definition. So you can straight away use the Laplace table. Alright, let me give some more example. Okay, if I have Laplace transform of t plus 1 cube. Okay, so basically you can expand this t plus 1 cube, so you will get t cube plus 3t square plus 3t plus 1. Okay, so you can separate them by the first linearity property. So I will have Laplace transform of t cube. So 3 is just a constant. I can take out 3 Laplace transform of t square plus 3 Laplace transform of t plus Laplace transform of 1. Okay, so we have now a Laplace transform of a function t to the power of n. So refer back to the table. So we will refer to this one, t to the power of n. Okay, so your n can be 0, 1, 2. So we get n factorial over s to the power of n plus 1. Okay, we go back to our example. So we have t cubed. So in this case, my n is equal to 3. So I will get 3 factorial over s3 plus 1 plus t square, n is equal to 2. So 3 multiplied by 2 factorial over s2 plus 1 plus 3. So t, which means n is equal to 1. So I have 1 factorial over s1 plus 1 plus Laplace transform of constant. I will get 1 over s. So the answer will be 6 over s power of 4 plus 3. Okay, 2 factorial is 2. So I have 6 over s cubed plus 3 over s squared plus 1 over s. Okay. Another example is what if I want to find a Laplace transform of sine AT, okay, using linearity property. So they don't want you to get it straight from the table, and they don't want you to get it from the definition. They want you to use linearity property. So first, you must recall that sine AT is equal to 1 over 2 multiplied by exponent AT minus exponent negative AT. So this is the definition of hyperbolic function you have learned in engineering mathematics 1. So Laplace transform of sine AT is equal to Laplace transform of 1 over 2 multiplied by exponent AT minus exponent negative AT. Right, so 1 over 2 is just a constant. You can take out. So 1 over 2 Laplace transform of exponent AT, okay, minus Laplace transform of exponent negative AT. Okay, so you can refer to the table. Exponent 1 over 8, exponent AT is Laplace transform of exponent AT is 1 over s minus a minus, so now minus a, so you have s minus negative a. So this is equal to 1 over 2 s minus a minus 1 over 2 s plus a. Okay, so this can be written as 2s plus 2a minus 2s minus 2a divides by 2 s minus a s plus a. Sorry, we have another 2 here. So we get 2s plus 2a, so we can cancel out 2s. So we have 2a plus 2a. So we have 4a So for a over 4s minus a s plus a, so we can cancel out. This is equal to a over s squared minus a squared. So you can compare with the table. So Laplace transform of sine at is equal to this. Okay, so it depends on the question. So this question asks you to use linearity property, right? So I think alright, so that's all I think for the linearity property. So now we will move to the second property, which is first shifting property. Okay, so for first shifting property, we have that if Laplace transform of ft is equal to fs, so this is, we already defined that the Laplace transform of a function ft is denoted as fs, then the Laplace transform of, okay, so if I have exponential form multiplied by ft, so it will be equal to fs minus a, where a depends on the power of exponential form. Okay, so we can prove this first shifting property by definition. So if I have by definition, if I have a function ft, okay, it is equal to integrate exponent to infinity ft multiplied by it should be exponent negative st multiplied by ft and it is denoted by fs. So if I have Laplace transform of exponent at multiplied by ft, it will be equal to integrate 0 to infinity exponent negative st multiplied by exponent at multiplied by ft. So this is our function now, right? So here it is equal to integrate from 0 to infinity exponent negative t s minus a multiplied by ft dt. Okay, so this is improper, so we have limit k approved. Well, no need actually. So this is equal to 0 to infinity exponent negative p t multiplied by f t dt, where p is equal to s minus a, right? So if you see here, this is equal to fp, because here instead of exponent negative s, here I have exponent negative p, where p is equal to s minus e, so fs minus e. So this proof is just for your for the sake of your knowledge. Alright, so now let's try to use the first shifting property to solve this example. Find the Laplace transform of exponent to t multiplied by t. So if you see here, your a is equal to 2. So the Laplace transform of exponent to t multiplied by t is equal to fs minus 2. Okay. Alright, so what is your fs? So now this is your exponent. If you see in your Laplace exponent at, in your first shifting property, it will be exponent at multiplied by ft. So a is equal to 2, and you have to know what is your ft. So ft now is equal to t, because it should be Laplace of exponent at multiplied by ft, right? So fs is the Laplace transform of ft, and now our ft is equal to t. Okay, so by the table, you can refer to the table. T is equal to, so t to the power of 1, so n is equal to 1, so it will be 1 factorial divided by s1 plus 1 equal to 1 over s square. So therefore, Laplace of exponent to t multiplied by t is equal to fs minus 2. So this is your fs. Now you must replace your s with s minus 2. Be careful, you replace the whole term. So you replace 1 over s minus 2 square. Let me show you a common mistake that students always did before. Common mistake is when you put Laplace of exponent to t multiplied by t equal to fs minus 2 equal to 1 over s square minus 2. So this is wrong. You should see that we have the whole term in the bracket to be s minus 2. So here you must put a whole thing to be, you must replace your s here to be s minus 2. Okay, right, please do not repeat the same mistake. Okay, next example we have, okay, so in this next example we have exponent multiplied by cos. Okay, as I said previously, first we know that exponent at multiplied by ft, we use first shifting property. So now my a is equal to 4 and my ft is equal to cos t. So you must straight away know what is your a and what is your ft. Okay, so hence Laplace transform of exponent for t cos t is equal to fs minus 4. So this is by first shifting property. So to get fs minus 4, we must know what is fs. Okay, so fs is equal to Laplace of ft, where your ft is equal to cos t. So by the table, you know that Laplace transform of cos t is s over s square plus a square. Alright, in the Laplace table, it is written s over s square plus a square. But you must know that a is not this a. It depends on this a now. So your a here is equal to 1. So s square plus 1. Again, be careful, not this, not a from the exponential form. The a must come from the cos itself. So you have s square plus 1. Right? So therefore, Laplace transform of exponent for t cos t, okay, is equal to fs minus 4. So now you replace all term s here with s minus 4. This one and this one, all term s. So you have s minus 4 over s minus 4 square plus 1. Okay, because 1 square is equal to 1. Okay, so we have s minus 4 over s square minus 8s plus 16 plus 1. So equal to s minus 4 over s square minus 8s plus 17. Alright, so this is our final answer. So, oops, sorry. Another assignment for you. So this one will be assignment 3.2, number 1. Find the Laplace transform of exponent negative t cos 4t plus exponent negative 5t sin 3t. Right? Okay, so I will end our video now. In the next video, we will continue with the multiplication by t to the power of n. Okay.